this is Captain Chaudhari. In my series of videos on basic stability calculations, today I'm going to speak about form coefficients. In the form coefficients, the first two coefficients that we are going to discuss today is the water plane coefficient and the block coefficient. What is this water plane coefficient? Well, water plane coefficient is used to find out the water plane area at any draft. Let us look at the water plane coefficient. Suppose here's a ship and this is the water level, and if I cut the ship, assume that if I cut the ship along the water plane, I'll probably get a shape like this. Right? So this is the water plane area. This is the water plane area at this draft, right? So if I want to enclose this water plane area in a rectangle that is just fitting the water plane area, right? That means the breadth is equal to the maximum breadth and the length of the rectangle is the length of the water level over here. Then the ratio water plane area divided by circumscribing rectangle is coefficient of water plane area. So this is the coefficient of water plane area. As you can see that the water plane area has to be always less than the area of circumscribing rectangle. So water plane coefficient is always less than 1. It cannot be more than 1. Let us now do a numerical from my book, that is basic stability calculation. Find the water plane area of a ship for a draft at which the length is 106. Length is equal to 106 meters. The breadth is 21. And coefficient of water plane is 0.84. CW is equal to 0.84. So very easy, water plane area divided by 106 into 21. Water plane area divided by L into B should be equal to 0.84. So water plane area is equal to 106 into 21 into 0.84. into 21 into 0.84 gives me 1869.84. 1869.84 meters square. Now we can also find out the TPC from this. TPC is nothing but water plane area into 1.025 divided by 100. So it should be 18.6984 into 1.025 gives me 19.166. 19.166. So this is a simple numerical to understand the relationship between the water plane coefficient, the length breadth of the vessel, and TPC. We can find out the TPC once we know the water plane area. When I ask the students like what are the different ways in which you can find out the water plane area, typically there are some students who say that we know the underwater volume of the ship, we know the draft of the vessel. Underwater volume divided by draft is water plane area. Absolutely ridiculous. There are 3 ways to find out the water plane area. Let's look at them. The best way to find out the water plane area is TPC. TPC at any draft is known from the hydrostatic tables. So 100 TPC divided by 1.025 is actually water plane area. In a pre-C institute they teach what is TPC, but the students just know what is TPC. Practically a sailing master, if I ask him how to get water plane area, he does not relate it with TPC. So stability that we learn must be usable practically. So this is the best way. Or suppose TPC of your ship is 50. It means that water plane area is approximately 5,000 meters square. If you want accurate, then divide it by 1.025. But basically one must know that approximately 100 times the TPC is the water plane area. This is one method. The second method, which I told you, is length into breadth of the rectangle circumscribing the water plane area multiplied by water plane coefficient is also water plane area. The third method is Simpson's. Suppose we have the transverse ordinates, we can find out the water plane area by Simpsonizing, and if we have taken the moment about the aft perpendicular, we can also find out the LCF, that is the distance of center of flotation from aft perpendicular. So these are the different ways in which we can find out the water plane area at any draft. Let us now learn what is block coefficient and how block coefficient helps us to find out the underwater volume of the ship. Here's a ship. Let us say this is the water level. Now, if we consider just the underwater portion, say at summer draft, suppose this is summer draft. If we just consider the underwater portion, if we want to fit it in a box whereby this underwater portion just fits, then it is clearly visible here that the box or cube we are talking about, the cuboidal that we are talking about, is just about able to accommodate the underwater portion. Now such a box, what is the volume of the box? The volume of the box would be length into breadth into draft. Whereas the underwater volume is the volume of the block which is inside, that is the underwater portion of the ship. Now ratio is called block coefficient. So block coefficient can be defined as the underwater volume on a certain draft, typically the summer draft, divided by length into breadth into draft of, these are the dimensions of a block which is just about able to accommodate the underwater volume, underwater portion, or it is volume of box that is circumscribing the underwater portion of the ship. So this is the block coefficient. Block coefficient, like water plane coefficient, has to be always less than 1, right? So let us do a numerical from my book about the block coefficient, right? So here is the question. A ship 130 feet, a ship 134 meters long with a beam of 26, has a summer draft of 9.48 meters. That is a summer draft. The block coefficient at this draft is 0.68. CV is 0.68. Which says find the summer displacement. So the summer displacement would be underwater volume into 1.025. But how to get underwater volume? Underwater volume should be equal to length into breadth into draft into block coefficient, which is 0.68. So that would be 134 into 26 into 9.48 into 0.68. So 134 into 26 into 9.48 into 0.68 gives me underwater volume as 224592.58, and this, if I multiply with 1.025, gives me displacement. So displacement is nothing but 23020.74 tons. This is how I find out the underwater volume and displacement of the ship. The block coefficient method, when you know the block coefficient at a particular draft. Another one, which is the most practical one, is look at the displacement from the hydrostatic tables for a draft, and then displacement divided by 1.025 will give you underwater volume at that draft. But there are one or two other ways also to find out the underwater volume. We will discuss them right now. So one method is, suppose here is a ship. Let's take a simple. Now we are talking about the water lines. At different water lines, if we know the plan view at different water lines, right? If we know the plan view at different water lines, and if we Simpsonize, taking the first ordinate at the bottom ordinate is the first ordinate, right? And then as the draft increases, we take more and more water plane area. If we Simpsonize these water plane area and the bottom ordinate is the first ordinate, and we take the moment about the bottom ordinate, that means if we take the bottommost ordinate WPA 1 and this one as WPA 2 and the third one as WPA 3, etc. And if the difference of drafts is 1 meter, then the distances would be 0, 1, 2, 3 meters, etc. And we Simpsonize and then take the moment also about the bottom ordinate. Then what we will get after Simpsonizing is, like if you Simpsonize the water plane area, you are going to get volume, underwater volume. So we get underwater volume, and because we have taken moment about the bottom ordinate, that is the base ordinate, we will also be able to get kb. So this is the method to find out the underwater volume and kb. The method is Simpsonizing. And how do you get these water plane areas? These water plane areas, as I told you, can be found out from the TPC. There is yet another method to find out the underwater volume. Suppose this is the water line and we divide the ship into various sections, right? At different sections, the area would appear this way. Suppose, and we find out all these areas at this draft, at this trim. The information, of course, is available from the Bonzine's curve. We must have heard about the Bonzine's curve. So Bonzine's curve gives you the transverse underwater area at a given draft, at a given trim, right? So if we Simpsonize all these areas about the half perpendicular or the aftermost ordinate, what we can get is the underwater volume. And also, because we have taken the aft ordinate as the first ordinate, if we take the moments about the aft ordinate, we can also get the LCB. So this is yet another method to find out the underwater volume and LCB.